Chapter 7, Acid and Bases.
Arrhenius concept of acid and base.
Arrhenius, a Swedish chemist, was the first to define acid and base in aqueous solution.
According to Arrhenius, an acid is defined as a substance which contains hydrogen and which, when dissolved in water, give hydrogen ion. Accordingly, all mineral acid HCl, HNO3, H2SO4 contain hydrogen and when dissolved in water dissociate completely into hydrogen ion. Arrhenius named these acids which dissolved completely in water as strong acid. There are other acids like acetic acid, carbonic acid, and phosphoric acid, which when dissolved in water do not dissociate completely into ion. As a result, an equilibrium is set up between the ions and the undissociated acid molecule. Arrhenius named these acids as weak acid. According to Arrhenius, a base is a substance which contains hydroxyl group and which when dissolved in water give hydroxyl ion. The substance like NaOH and KOH which when dissolved in water dissociate completely to give hydroxyl ion. Arrhenius named these bases which dissociate completely in water as strong base. There are substances which do not completely dissociate into hydroxide ion. Arrhenius named these substances in weak base. For example, substances like NH4OH, MgOH twice, AlOH thrice do not dissociate completely to give OH negative ion and can be written as hydrogen ion obtained from the acid and hydroxyl ion obtained from the base taken together to form unionized water. Arrhenius describes this combination of H positive and OH negative ion as neutralization reaction. Arrhenius concept is very simple to apply and explain a number of phenomena like neutralization, hydrolysis of salt, strength of acid and base. However, there are certain limitations which are described below. Arrhenius concept of acid and base is applicable only in aqueous solution. This concept to explain the acid and basic behavior of substance in non-aqueous medium such as ammonia, liquid sulfur dioxide, alcohol, etc. Arrhenius concept failed to explain the acidic character of substance like CO2, SO2, SO3 and the basic character of substance like NH3, Na2, CO3, CaO, etc. Arrhenius concept also failed to explain the reaction between an acid and base in the absence of water. Although Arrhenius concept of acid and base suffer from a number of limitations, yet the concept is very useful and informative for an elementary approach. Bronsted-Lowry concept. Arrhenius concept of acid and base are further improved by Bronsted and Lowry. Both Bronsted and Lowry in 1923 incidentally introduced the same definition of acid and base. According to Bronsted-Lowry concept, an acid is a substance which can donate a proton, whereas a base is a substance which can accept a proton. In other words, an acid is a proton donor, whereas base is a proton acceptor. As a result, Lowry-Bronsted concept is sometimes called the proton donor receptor concept. According to Bronsted-Lowry, a neutralization reaction involves the release of the proton by an acid and the acceptance of that proton by a base. For example, the reaction between HCl and NH3 to form the salt ammonium chloride can be represented as the curved arrow show how electron must rearrange to result in the transfer of hydrogen atom from the acid to a base. The unshared pair of electron on the nitrogen of ammonia is attracted by the partial positive charge on the hydrogen in the polar hydrogen chloride molecule. A comparison of the structure of the reactant and product show that the hydrogen atom which was bonded to chlorine in the reactant is bonded to nitrogen in the product. The subproton has been transferred from chlorine to nitrogen to act as a Bronsted-Lowry base. A species must have at least one unshared pair of valence electrons so that it can form a covalent bond to the proton. To act as a Bronsted-Lowry acid, a species must contain at least one hydrogen atom that is attached to an atom that is more electronegative than hydrogen. In this case, HCl loses a proton and is an acid. Ammonium accepts a proton from HCl and is a base. Ammonium ion NH4 positive has a tendency to donate a proton. In other words, an acid donate a proton and become a base, and a base accept a proton and become an acid. In the above example between HCl and NH3, Cl negative is the conjugated base of HCl and NH4 positive is the conjugated acid of the base NH3. Acid and base that are related by the loss or gain of H positive are called conjugated acid and base pair. It is clearly indicated that any acid-base reaction would involve two acids and two bases. These acid and bases are called conjugated pair. In the above example, HCl is an acid since it donates a proton and Cl negative is conjugate base. Water accepts the proton and hence is a base, thus H3O positive ion is the conjugated acid. A strong acid has a weak conjugate base. A substance is capable of showing acidic character only if the other substance is capable of accepting the proton. For example, HCl is an acid in aqueous medium because water can accept the proton from HCl. However, HCl is not an acid in benzene because benzene does not accept H positive ion from HCl. Not only neutral molecule but cation and anion may act as acid or bases. Both Arrhenius and Bronsted-Lowry concept require an acid to be a source of proton. Thus, all Arrhenius acid are Bronsted-Lowry acid. According to Arrhenius, a base is a substance which gives OH negative ion in solution. Whereas according to Bronsted-Lowry, a base is a substance which can accept a proton. Carbonate ion CO3 2 negative cannot give OH negative ion in aqueous solution. It is therefore cannot be a Arrhenius base. Thus, all Bronsted-Lowry bases are not Arrhenius bases. Limitation of Bronsted-Lowry concept. Although Bronsted-Lowry concept could explain the shortcoming of Arrhenius concept, yet it could not answer some of the well-established reactions. For example, it cannot explain the reaction between acid oxide like CO2, SO2 and SO3 with the basic oxide like Ca2, CaO, BaO and MgO, which take place even in the absence of water. Clearly, in the reaction between CaO and SO3, there is no proton transfer involved in the reaction. The acid nature of compound like BF3, FeCl3 and Al3. Lavish concept of acid and base. G.N. Lavish in 1923 proposed a more general definition of acid and bases which is based upon the donation and acceptance of electron pair. According to Lavish concept, an acid is a substance which can accept a pair of electrons. A base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor. It means that a substance which has vacant orbital to accommodate one or more pair of electrons can act as a Lavish acid. On the other hand, a base is an electron pair donor. It means that any substance with unshared pair of electrons can behave as a Lavish base. Thus, the acid-base or neutralization reaction involves the formation of a coordinate bond between the electron pair donor and the electron pair acceptor. For example, the reaction between boron trifluoride and ammonia is a typical Lavish acid-base reaction. Lavish acid. According to this concept, Lavish acids are classified as molecules having central atom with incomplete octet of electron. Boron trifluoride, aluminum trichloride are acids of this type. It is clear that the central boron and aluminum atom has only 6 electrons. Simple cations. All the cations are short of electron and can behave as Lavish acid. Larger the cation like Na positive, K positive, Ca2 positive and Ba positive etc. behave as weak Lavish acid. This is because these have little tendency to accept electron. On the other hand, small size cations such as H positive, Ag positive and Li positive ion have a strong tendency to accept the pair of electron, and a strong Lewis acid. In addition, highly charged cation have a higher tendency to accept electron pair related to lower charged cation of the given metal. For example, SN4 positive is a strong Lewis acid than SN2 positive. Molecules with multiple bond between atoms of dissimilar electronegativity. Carbon dioxide represents an interesting example of a double bond between carbon and the more electronegative oxygen atom. Oxygen, being more electronegative, has a tendency to attract the shared pair of electrons more toward itself in CO2. As a result, it acquires positive charge on the carbon atom and becomes electron deficient. Lewis base. According to this concept, Lewis base may be classified as one of the following type of substance. Negatively charged anionic species. All the negatively charged species are Lewis bases because they are rich of electron and have a strong tendency to donate electron pair. The greater the charge density on the anion, the stronger is the base. Neutral molecule with one or more than one unshared pair of electron. Molecule with unshared pair of electron as Lewis base. Alkene or alkyne with multiple bond also form coordination bond with metal ion and organometallic compound. Acid-base reaction according to Lewis concept. Some of the typical acid-base reaction involve the formation of a coordinate bond between a Lewis acid and Lewis base are summarized below. Lewis acid-base concept discussed above is widely used because of its simplicity in understanding many acid-base reactions. In spite of its wider applications than Arrhenius and Bronsted-Lowry concept, it has several disadvantages which are discussed below. Lewis concept is too general and consider all reaction forming a coordinate bond to acid and base reaction. This is however not true always. According to Lewis concept, some of the transition metal that form compound with carbon monoxide such as etc. are acid-base reaction, which is not correct. Formation of a coordinate bond between an acid and a base is the basis of Lewis concept. However, the well-known acid like HCl, HNO3, H2SO4 do not form coordinate bond with the base such as NaOH or KOH. Accordingly, HCl, HNO3 and H2SO4 should not be regarded as acid according to Lewis concept. Lewis concept does not give any uniform scale of acid-base strength. Lux-Flood concept of acid and base. A new concept of acid and base was proposed by Lux in 1939. This concept was further extended by Flood. According to Lux-Flood concept, an acid is a substance which accepts an oxide ion, whereas a base is a substance which gives up oxide ion. According to Lux-Flood complex, a substance that shows a tendency to lose as well as gain an oxide is called amphoteric. Zinc oxide represents an interesting example of amphoteric character. Solvent system concept. The solvent system concept of acid and base was postulated by K.D. Astley in 1928. It is an to the Lowry-Bronsted concept and is applicable to both protonic as well as non-protonic solvent. According to this concept, an acid is a substance which either by direct dissociation or by interaction with the solvent give a cationic characteristic of the solvent. A base is a substance which either by direct dissociation or by interaction with the solvent give the anionic characteristic of the solvent. The characteristic cation and anion of the solution are the ions produced during the autoionization. The prefix auto means itself. To illustrate this concept, let us consider the autoionization of some of protic and non-protic solvents. For example, HCl behaves as an acid in water solvent as it gives the cationic characteristic. Similarly, NH3 acts as a base in water as it gives the anionic characteristics of water. It is important to note that acetic acid behaves as an acid in water as it produces the cationic characteristics of water. Acetic acid behaves as a base in sulfuric acid as it produces the anionic characteristics of solvent sulfuric acid. Urea dissolve very readily in water and give neutral solution. However, urea dissolve in liquid ammonia and behave as an acid because it gives the cationic characteristic of the solvent. Similar to Arrhenius concept, neutralization reaction may be represented as the combination of cationic characteristic of the solvent with the anionic characteristic of the solvent to form the solvent molecule. Types of solvent. Solvents are classified in a number of ways on the basis of their physical and chemical properties. Broadly, there are three ways in which the solvent can be classified: protic and non-protic. Aprotic solvent. Solvent which contain hydrogen and can lose hydrogen in the form of proton are called protic solvent. Common examples are H2O, NH3, H2S, HF, etc. Solvent from which hydrogen cannot be obtained in the form of proton are called aprotic solvent. Acid and base and amphoprotic solvent. Solvent which have a strong tendency to give proton are called acidic, which have strong affinity for proton are called basic solvent. Solvent which display both acidic and basic properties are called aproprotic solvent. Ionizing and non-ionizing solvent. Solvent which undergo self or auto ionization are called ionizing solvent. Example are water, ammonia, hydrogen fluoride, sulfur dioxide, etc. Relative strength of acid. The strength of protic acid can be compared easily with the tendency of the acid to give proton. Protonic acid like HCl, H2SO4, HNO3 ionize completely to give proton, whereas acid like CH3, COOH, HF, and HCl ionize incompletely to give proton. The acid which ionize either completely or to a very large extent are named the strong acid. On the other hand, acid which ionize to a smaller extent are named weak acid. The protonic acid, namely HCl, H2SO4, HNO3 are strong acid, and CHCl, CHCOOH, HF, and HCl are weak acid. It is the extent of ionization of an acid which measures the strength of acid. A large value of pK means that the acid is little dissociated. It implies that the acid is weak. Thus, larger the value of pK, the weaker is the acid. Thank you.